quantum mechanics is just kind of irreducibly weird. And studying philosophy means you can be philosophical about the fact that it's weird. I realized just from talking with folks who did things like NMR that you could actually do a Toffoli operation in a very straightforward fashion. If you just have 3 qubits that are interacting with each other, then there's a simple procedure that will allow you to flip this one if and only if these other 2 are 1. Plagiarism is the most sincere form of flattery. And self-plagiarism is even more sincere. Of course, my favorite quantum computer is the universe itself.
The 632-nanometer team sits down with MIT professor Seth Lloyd in Cambridge, Massachusetts for a mind-bending journey through quantum mechanics, information theory, and the early days of quantum computing. Lloyd shares fascinating stories from his pioneering work in quantum information, including how he nearly got expelled from his PhD program for pursuing what was then considered a crazy research direction. Through engaging examples and personal anecdotes, he explains why quantum mechanics is irreducibly weird, and how information and entropy are fundamentally the same thing. The conversation takes unexpected turns with remarkable stories about Stephen Hawking's quantum gravity lectures, Richard Feynman's 3 tricks that revolutionized physics, and epic MIT student pranks including the great Caltech cannon heist. Lloyd also tackles deep questions about consciousness, free will, and the computational nature of the universe, explaining why the universe itself may be its own most efficient simulation.
Seth, you are known, first of all, as the great physicist and quantum mechanical engineer. But it's an interesting fact from your past that you also have a degree in philosophy and history. Could you tell us, how did it happen?
Yeah, it's funny, like my graduate degrees are in math, physics, and philosophy. And now I'm not only a professor of quantum mechanical engineering, I'm really kind of a quantum mechanic. Like, your quanta are broke, we fix them. And we charge a lot of money for that because there are not so many of us, right? And it's bad to have broken quanta. That came about rather accidentally. I was on a Marshall Scholarship at Cambridge. I did my undergraduate degree in physics at Harvard and graduated in 1982. And the next 2 years I was at Cambridge. And the first year I did Part 3 maths, which is basically a master's degree in theoretical physics. And I didn't know what to do the second year. It was all paid for. So I'd always been interested in information theory when I was an undergraduate. And also I never really understood quantum mechanics that well. Like when Norman Ramsey, whom I learned quantum mechanics from, when he was writing these notions of electrons being in 2 places at once and stuff like that, that never made any sense to me. And so I kind of figured that maybe if I studied the philosophy of quantum mechanics while focusing on ideas of information theory, that maybe it would make more sense afterwards. Of course, that wasn't true, because it turns out that quantum mechanics is just kind of irreducibly weird. And studying philosophy means you can be philosophical about the fact that it's weird. So it remained counterintuitive, but I set down this path of looking at ideas of information and mutual information, quantum mechanical systems and entanglement, and this was very productive. I started thinking about ideas of quantum computation at that time, because the idea of quantum computation had just been created in the early 1980s. Then that led me to where I am right here, talking with you guys.
Was there someone, like a scientist, whom you were inspired most?
Well, I was lucky that the philosopher Jeremy Butterfield, who's a philosopher of physics, who took me on to supervise my MPhil thesis, he said, "This is cool, just go and do this." I've had the privilege to work with a lot of people. Not only did I study quantum mechanics with Norman Ramsey, but as an undergraduate, I also worked for him for 1.5 years in his labs, both at Harvard and at his famous electric dipole moment of the neutron experiment in France, in Grenoble. I worked for Carlo Rubbia at CERN. When I was there, when they discovered the W particle, that was really great. I take full responsibility. I made good coffee, and my solder joints were excellent. So I don't know why I'm not on the paper along with them. And then my first postdoc I did with Murray Gell-Mann, who was really an amazing scientist and a wonderful and very frustrating person to collaborate with.
Frustrating, how so?
Well, Murray won an unshared Nobel Prize in high energy physics, I think in 1968 or something like that, for all of the things he'd done, like strong interactions, electroweak interactions. And he was unaccustomed to publishing results when you have them. So those folks in high energy theory, often they'd only end up writing like a dozen or so papers during their lifetime. and they would wait for a long time for doing it. And we were deriving all these results and ideas about information and complexity and quantum information. I said, hey, we got the result. Let's just like pop it out there. And we were like, oh, no. We have to think about this for another 6 years. It's a little frustrating.
So he wasn't worried that he would get scooped or anything.
Oh, the stuff we were doing was so profoundly unpopular. Getting scooped would have been a very unlikely. Indeed, one of the whole features about ideas about quantum mechanics and information theory, because the ideas about information quantum mechanics were associated with foundations of quantum mechanics, which at the early 1980s was considered to be a really bad field. Like physicists didn't like it. This was like kind of the central part of the shut up and calculate philosophy of quantum mechanics. And indeed, 2 years into my time at Rockefeller, where I went to go do my PhD, I was working on ideas of complexity, mutual information. I was proving the theorem, which eventually became Page's theorem, showing that mutual information rises to its maximum value in entangled systems. And 3 full professors came to my office and kicked out of my office mate and said, okay, Lloyd, we don't understand what you're doing, and actually we don't care. So if you want to keep working on this crazy stuff, you can leave. Go somewhere else. If you want to stay here at Rockefeller, you can work on this extremely dull problem in 2-loop calculation and weak interactions. So it's like, whoa, okay. Yeah, so it was profoundly unpopular then. Indeed, one of the fun parts about quantum information theory, now that it's actually quite a popular theory and very useful, is that it's kind of rehabilitated the theory of foundations of quantum mechanics.
Do you think there are cultural preferences between the UK and the US? Because I do feel like the UK does prefer topics in foundations a lot more.
Yeah, the philosophy of physics departments, both at Cambridge and at Oxford, where I've also had the pleasure to be a visiting professor, are really excellent, and they've got the right idea of things, and it doesn't seem to be a problem there.
What brought you more like to this, as you said, non-mainstream area of quantum information? Because you said it was mostly physicists at that time were like focused on like more fundamental kind of problems.
Yeah, so I was very frustrated when I was an undergraduate at Harvard. Ever since my sophomore year, or perhaps it was my junior year, I took statistical mechanics with Michael Tinkham, who was a really great teacher. He emphasized that the basic formula for entropy and the formula for information were one and the same. And indeed, when Claude Shannon, came up with the mathematical theory for information, he said, he went to John von Neumann and he said, hey, I've got this quantity minus some p log p. What should I call this? Von Neumann said, oh, you should call that h, because that's what Boltzmann called it, in Boltzmann's famous H theorem. So in fact, the basic formulae of information theory were derived by Maxwell, Boltzmann, and Gibbs back in the 19th century, and to refer to entropy. So I was very frustrated with the proofs of the second law that entropy had to increase, starting with Boltzmann's H theorem, which Boltzmann said, well, under the assumption of what he called molecular chaos, that when 2 molecules or atoms collide, they're uncorrelated, as if they've never collided before or collided with other molecules that have interacted with them. That's obviously not true. In order to prove the second law, Boltzmann had to assume that. And then you get, okay, yeah, entropy increases. But right away, Loschmidt said, hey, that can't be true because we know that the underlying laws of classical mechanics are reversible. So you let these molecules collide with each other and entropy looks like it's increasing. And if you were just to reverse all their velocities, they'd go back to the little corner of the box where you started them in the first place. So it can't possibly be true. To which, what Boltzmann said to Loschmidt when Loschmidt said that? He said, go ahead. Reverse them. It was kind of Boltzmann's Clint Eastwood moment.
Yes.
Like, make my day. Yeah, so, and of course there's a good reason for this, which is not to get too geeky right away, but both in classical mechanics, the time evolution of the underlying probability distributions is unitary. Mm-hmm. And in quantum mechanics, the time evolution of the underlying quantum states is unitary. And unitary evolutions just don't change the entropy. I mean, if entropy is a way of counting the number of different states you have, and Planck's original formula, which is written on his grave, I'll go up and draw a picture of what it looks like, something like this. I forget when he exactly was born, something like 1848, he died in 1906. And then, actually, it's got a scary looking picture of his face if you go and look at it, but then it says S is equal to K log W. Mm-hmm. And Sorry, excuse me, this is not Planck's grave. This is Boltzmann's grave.
Boltzmann,
Boltzmann, not Planck yet.
who died by his own hand, right?
Was that the reason of his dramatic ending?
Well, actually, this formula is like, it's kind of slightly, Boltzmann
Cursed.
would not like that because Boltzmann, he didn't write down this formula. K, of course, is what we now call Boltzmann's constant, 1.38 times 10 to minus 23 joules per degree Kelvin. But actually, that constant was defined by Planck. So Boltzmann just like, in his figuring out that entropy was proportional to the logarithm of the number of states of the system, then he didn't know what the constant was. And Planck, it took to Planck to actually derive quantum mechanics or suggest quantum mechanics, which he did exactly for the purposes of defining entropy correctly. And then, so he was able, by looking at black body radiation and under the assumption that energy is quantized, he was able to derive the actual value of Boltzmann's constant we know today. And indeed, this constant K was called Planck's constant, along with what we call Planck's constant. And then
H bar.
Yeah, sometimes I think like sometimes in the 19-teens, Ehrenfest said, hey, this is too confusing. We can't have two Planck's constants. Let's just call the other one Boltzmann's constant. Yeah, I think if Boltzmann saw this, you know, if he were alive today, he'd be rolling over in his grave if he saw this.
Maybe could you give some more of intro into entropy, like let's say for those who are not really familiar with statistical mechanics? I think it's fascinating. When I was reading your book with all the details and how is it introduced, what would be great
Yeah,
to
sure.
hear as well.
I mean, maybe the simplest way to think about this. So entropy is information. In my freshman course on information, I say information is information we know, and entropy is information we don't know. Right. So information in our digital era, and people know that, you know, the fundamental unit of information is the bit, which just represents the difference between two possibilities, like yes or no, or true or false. When George Boole originally came up with the idea of Boolean logic, it was all based on bits, but back in the 1840s, and he was using true and false because he wanted to see how you can make precise statements of mathematical and logical propositions, and it's fundamentally digital. That's why I call it Boolean logic. If you have one bit, it has two states. If you have two bits, you know, let's call them 0 and 1, because that's what people tend to do now. If you have two bits, then you have four states, 0, 0, 0, 1, 1, 0, and 1, 1. If you have three bits, you have 8 states, you know, 0, 0, 0, 0, 0, 1, 0, 1, 0, etc., up to 1, 1, 1. And so the number of states grows exponentially as the number of bits. It goes as 2 to the number of bits. And Boltzmann's formula, which again predated all this notion of information theory, he realized that actually that this formula for entropy is the same thing, right? Because if the number of bits, if the number of states is 2 to the number of bits, then the number of bits is the logarithm of the number of states, right? And that's just what Boltzmann's formula says. Boltzmann's formula says that entropy is proportional to the amount of information required to describe the unknown state of some system, like the positions and velocities of all the molecules in this room defined up to the accuracy allowed by quantum mechanics. So information is at bottom entropy, and entropy is at bottom information.
Given your expertise in the field, do you actually get a lot of crackpot emails trying to convince you that you can somehow circumvent the second law?
Yes.
How
is
do
the
you
answer to that.
how do you typically how
Fact
do you
that-
try to poke holes into it?
Well, I do miss the days. I have to say, this has been going on for a long time, the contact with crackpots, and I do miss the days when people would just send you, get these big envelopes and you'd open it up and they'd be full of pages and pages of hand-drawn crazy pictures. In that filing cabinet over there's a file called unsolicited material, which has these things that people would send you. I feel that email deprives crazy people of their true medium. So yeah, I do get a lot of those. Actually, I respond to emails like that if the person honestly seems to be doing a good job. The emails I try always to respond to are ones from people who are, for instance, in high school or in college, and they say, hey, I've got this question, what the heck is going on? Just responded to a few of those today. But then perhaps these high school students are less crackpotty than some of their older colleagues.
Right?
Where does the quantum mechanics come? So we have like statistical mechanics, like entropy,
Yeah.
and there's a Boltzmann formula. Where do you go after that?
Really, what I was doing for the first few years, starting my MPhil and then all through my PhD thesis, was pursuing this idea that I had had at the beginning of doing my MPhil, which is the overall entropy. So why is it difficult to show that entropy increases? It's because entropy is the logarithm of the number of states. So if I can be in one of 4 states, I've got 2 bits of information, I'm missing 2 bits, and I don't know which one it is. And so then if the dynamics is 1 to 1 and onto, so if the dynamics takes each possible input state to exactly one output state, then if it can be in one of 4 states before the system is involved, then it can be in one of 4 states afterwards. So the entropy is the same, like the logarithm of the number of states is the same. That's a fundamental problem with proving the second law, because the actual entropy doesn't change. And indeed, when we look at the universe as a whole, then it's what we see from cosmological observation is consistent with the overall entropy of the universe being 0. The universe started in a pure state during inflation before the Big Bang, and by gosh, it's still in a pure state, right? So then what's going on? So the idea that I had was that one thing that is not constant is the amount of mutual information between the parts of a system. So for instance, mutual information is information that's held in common. So for instance, if I have 2 bits, this one could be either 0 or 1, so it's got 1 bit of entropy, if you like. And I have another bit, which could also be 0 or 1, but they always show up in the combination 0, 0 or 1, 1. Then each bit on its own has a bit of entropy, 1 bit of entropy or 1 bit of information. But the 2 bits together actually also only have 1 bit because they can only be in 2 states, 0, 0 or 1, 1. The mutual information is the difference between the sum of the individual entropies minus the total entropy. And what you can show in my master's thesis and PhD thesis, I showed rigorously that if you take, say, a pure quantum state whose entropy is 0, and then it interacts with the different pieces interact with each other in a way, the overall entropy is still 0, but the mutual information between the parts of it tends to go up to its maximum value. So this is my proposed solution to the second law, and that you can actually prove without actually having to make all these kind of fake assumptions that Boltzmann and other people did.
Is it true that the universe started from just a single bit? I guess there's like a lot of mysteries about the moment of the Big Bang and how everything, started to appear and evolve. What are the assumptions about the entropy?
Well, it
at
could
the
be even
beginning?
less than a bit, right? Because it could be, and certainly many physicists and philosophers have speculated about it. It could be that there's only one possible initial state for the universe, and the number of bits in one state is log of 1, which is 0. It's 0 bits of information. So it could start from no information whatsoever, right? And indeed, that kind of looks like that. What Alan Guth's theory of inflation, which has considerable amount of experimental evidence for it, says that prior to the Big Bang, the universe was in a pure state, which was the vacuum state, but the vacuum had a lot of energy because it was the most symmetric state, but not the lowest energy state. And this caused it to expand exponentially rapidly. And this gives good explanations for what we see cosmologically. But then, in fact, the part that we see within the visible universe, that all came from a pure state to begin with. So indeed, that wouldn't be the situation where there were 0 bits of information to start out with.
Is that something that philosophers of science get very worried about?
Well, I don't know about worried about it, they get head up about it.
Upset
Yeah,
about it.
maybe, I don't know. I'm not sure why that would make one upset. The whole notion of the Big Bang was first proposed by, it was Telly de Chardin, right, who was a Catholic priest. Mm-hmm. And he was, in his own mind, he was kind of explicitly, thinking of creation from nothing as being in a religious way as well as a physical way. Anyway, I don't take a position on the religious aspect of this, but it seems to me perfectly fine for the universe to have come from no bits of information to begin with. Mm-hmm.
Yeah, there is a fascinating point of view that actually also universe is the computer, also maybe a little bit detailed. It's a quantum computer. How did you get to looking at the universe in this way?
Yeah. So at the same time, I was doing this MPhil in History and Philosophy of Science at Cambridge, 83 to 84. I was taking Stephen Hawking's graduate seminar in quantum gravity, which was very fun. And he was talking about things like, for example, inflation and, what is the vacuum state of the universe and things like that. I'll tell you a little story about this. This was certainly one of definitely the most dramatic moment I've ever experienced in a classroom. So this was in the old Department of Applied Math and Theoretical Physics, DAMPT, which was on Silver Street. It was an ancient building. And the room in which the seminar was taking place was a small lecture theater with seats going around, and then big blackboard. In front of the blackboard, there was a platform, which is called a dais. It's about this tall, 1.5 feet tall. And the point was that the person lecturing could then stand on the dais and be better seen by the people there. Well, in Hawking's case, this was when he could still speak, but only people who knew him well could understand it. So he couldn't lecture. He had someone else who would translate for him, both translate what he's saying and write on the board. This fellow who was one of Hawking's postdocs, and he liked to wear like a pink jacket and like tinted spectacles and stuff. He was quite a good look. So Hawking would say, and then the postdoc would say, Professor Hawking says, this lecture is about the edge of the universe. The edge of the universe is very far away, but we can draw it like this. And then, he'd go up to the board and he'd start drawing like Penrose diagrams and things like that allows you to like bring in the infinite edge of the universe to where we can actually talk about it mathematically. And it was very fun and very good lecture. The lectures were great in this course because, first of all, Hawking was a very clear lecturer. And then I think just as important is that everything had to be said twice. So you had time actually to write it down, which was nice. Anyway, the lectures were maybe an hour and a half long or a couple of hours long. Hawking was excited about this work because it was the work he was working on right then. That's what his graduate seminar was about, to discuss the work he was working on with the graduate students, people. And so while the postdoc was translating and drawing pictures on the board, Hawking didn't have anything to do and he wanted to get on with it. So he was fidgeting. Well, so how do you fidget if you're Stephen Hawking? You can't even move, right? Well, so what he did, he's in his wheelchair and he puts his fingers on the little like knobs and he's going,
I can see it
sort of
coming.
nervously fidgeting while the postdoc is drawing stuff and talking. And then suddenly, like about 3/4 of the way in the lecture, there's a tremendous crash, and Hawking he's fidgeted his way to the edge of the platform, and he's like fallen off the edge of the platform. And there he is. He's in his wheelchair,
Oh, no.
like on the ground, like this. His like feet are like waving in the air, and it's like, oh my God, that's shocking. So a bunch of us, I get up. I was in the front row, so we get up and we like put that there. Like, Hawking back into his wheelchair, and Hawking is shaking. We're like, oh, he's gonna die right here. This is so horrible. No. Anyway, finally, it didn't take very long because it was clear that he wasn't about to die, and he was actually shaking from laughter. He wasn't even really hurt.
That's a great
And he
humor.
was just shaking from laughter, and he said, and the postdoc said, Professor Hawking says, fell off the edge of the universe.
That is quite unforgettable.
So that was very inspiring. And I really came upon the idea, working about these ideas about entropy and entanglement and mutual information. And while at the same time learning about, the state of the art in quantum gravity, I said, well, maybe, we could actually derive metric features of the universe, ideas of distance, from ideas of entanglement, like having an information-based metric or entanglement-based metric. And then you could perhaps derive something like quantum gravity by starting from that point and then seeing what it would take to make it reproduce general relativity and gravity at some classical level. And this is an idea I've been pursuing ever since. Now, well, yes, it's only 40 years later. It's okay.
Was this still before string theory?
So string theory. Yeah, so this whole notion of like for instance, now this is kind of like made its way entirely into the mainstream of things like ADS-CFT correspondence and string theory. But string theory was yet really to become. It had been developed, but it really didn't kind of hit its stride until a few years later, like the mid-1980s. And then everybody was doing string theory and promising they'd have all the problems of physics like wrapped up within a few months, which of course turned out to be wrong. Yeah, I mean, this is an idea. Now it's very popular. That point, it just was getting me kicked out of graduate school. So, but I guess you asked more about this idea of the universe and computation. So I actually came at this from indeed started approaching this whole set of questions about quantum mechanics and information to try to pursue notions of quantum gravity in the context of general relativity. There's some very nice papers from around that time from people like Ted Jacobson, for example, who had this notion of quantum gravity as a thermodynamic theory, right? And these are really nice papers. There's still great things about those. So it's only more recently that all the riffraff, the stringy riffraff, has come into the world. Now they somehow think it was their idea all along. Ha! Anyway, it's okay. I'm always happy when what is it? What do they say? Plagiarism is the most sincere form of flattery, and self-plagiarism is even more sincere. Yeah, so I started when I was doing my PhD and during the 1980s, and then doing my postdoc. I was pursuing these ideas about information. At the same time, I'd also decided round about like the late 1980s, kind of roughly when I got my PhD from Heinz Pagels at Rockefeller, and I went to Caltech to go work with Murray. I said, there weren't that many papers on quantum computing at that point. There were like 6. And I said, none of these are all very abstract. I wonder how you could build such an object. And so then at the late 80s, I started to try to say, well, how one might actually be able to construct a quantum computer. And I tried all kinds of stuff. Like actually the first thing I did was Feynman. Richard Feynman had gotten very interested in quantum computing in the mid 80s. And he'd written a nice paper. I mean, the idea of quantum computing had been proposed in the early 80s, 80 and 81, by Paul Benioff. And then Feynman got interested in it, and David Deutsch as well. And Feynman wrote a very nice paper in which he wanted these quantum computers to have a time-independent Hamiltonian. So he came up with an idea of including in the dynamics of the system a clock that would, like a program counter, that would count where you are in the computation. And he included this clock in his Hamiltonian. He was able to show that this would then, with this clock, you could have a time-independent Hamiltonian that would perform a quantum computation. So the first thing that I did was I realized I figured out how to diagonalize the Feynman Hamiltonian. And you can kind of see the argument. The argument is, well, if I have 2 quantum mechanical systems, they have the same energy eigenspectrum, so they look the same in diagonal form, then there's just a unitary transformation that makes them completely isomorphic to each other. So then if I can figure out what the Feynman Hamiltonian spectrum is, then I should be able to say, when can I make a system compute? Because if I have another quantum system that has the same spectrum and the same degeneracy of eigenstates, then I can make it compute. I mean, it sounds reasonable, right?
Simple, trivial.
It sounds reasonable. Yeah. Then what happened was I found a couple of things about this Feynman Hamiltonian. First of all, I was able to diagonalize it very easily, and its diagonal form was just the energy eigenstates for a free particle hopping along the line. The only thing that actually told you what the eigenspaces were the clock of this system. And that's sort of weird, because then how could it be that a free particle, maybe with some internal qubits, could actually be performing a computation?
So for Feynman Hamiltonian, is it the one which describes the three-body interaction or three-particle interaction, or what is
Feynman
like
Hamiltonian,
a good way to introduce it?
Yeah, do you want me? I can draw it.
Yeah, sure.
Yeah, sure. Yeah.
Yes, please.
So a quantum computation, the way that Benioff first talked about it, said, we have a sequence of unitary logic operations. So, so we have a set of qubits. Does it appear? Can you see it up there?
Yes.
Okay, good. And then you apply, the first logic operation, and then you apply the second one, then you apply the nth one. And for instance, this often can be written like in a circuit diagram form, and then, I have something where I rotate by pi over 3 around the z-axis, and then I do some more controlled knots and stuff like that. So, and then you put in the state 0, 0, 0, and you get out the state. We know u and 1 up to 0, 1, 0, 0, 0, and these perform the computation. So that's perfectly reasonable, but you can see it's a time-dependent system because all the u's are different, and you have to do them sequentially. So what did Feynman do? His Hamiltonian is he has this clock, And what the clock does, I'll label its position by L. And so it's just really, you can think of it as a particle that's just like hopping along a line. So it just hops along here.
It's like a random quantum walk, or?
Yeah, that's now, and right, this is the quantum walks didn't exist at that point. So this is what actually called, this is just a, this is the Hamiltonian says, oh, if I'm in the point L, I have to go to L plus 1. But you see that this is not Hermitian. So you have to add to the Hamiltonian, you have to add the thing that it's Hermitian conjugate, which has to go in the opposite direction. That's okay, but this is nothing. This is just a tight binding approximation for a free particle going along. And you could also, in contemporary parlance, say this is a Hamiltonian for a quantum lock along the line. So what Feynman said is, what we're going to do is we're going to adjoin. This is when the particle hops from L to L plus 1, then our bits, which are up here, we're going to perform UL on the bits. So we're going to do the Lth quantum logic operation. Could be like a controlled nod on like bits number 3 and 7 or something like that. And then to make this Hermitian, then you have to add this right here. So this is just the inverse operation where the clock moves back to here and you undo U sub L, right? And and the way that Feynman kind of originally thought of this is you set up this clock in a traveling wave packet that's going along like that, and here all your other bits are in the state 0, 0, 0, and then he was able to show that this clock would just essentially propagate through the computation, and at the end you would have the state which is this wave packet, now it's over here, but now we have the state U1, U2, UN for acting on 0, 0, 0. So you see that this clock kind of like just drags the whole computation through it. It's a sweet idea. Feynman, there's a great quote from Feynman. I won't get it exactly right. He said something like, I really only have like 3 tricks, but I know how to combine them in the right way, in a large number of ways. And this is one of his tricks, essentially, one of the 3 tricks that he knew that involves it. I don't know exactly how he used it in other ways, but it worked well. So the funny thing is that you guys are cool with this? I'm going to keep on physicizing.
Oh,
here
yes,
if you
no,
don't-
please.
you don't
No,
mind
this
giving mine
is
over.
fantastic.
Okay, great. I was able in 1990 or 1991, something like that. This is when I was said, okay, well, let's diagonalize this thing, right? And actually, it's not that hard. I'll call this HF. I was able by a series of sneaky tricks of my own, just to show that actually the eigenstates are pretty simple. So actually, first, if you just look at let's just look at the clock on its own. And here, let's say that this wraps around, so that this is also +1 is mod n. Now this is then is unitary. It's a unitary transformation that just takes, if you're in the state k, you go to k plus 1. If you're in 4, you go to 5. If you're 5, you go to 6. If you're up at n, you go back to n minus 1, you go back to 0, right? So it's pretty easy to see that the eigenstates of this are the following form. Sum from L is equal to 0 to n minus 1. And then we have L, and then we have E to the 2 pi I KL over n. Oops. And I'm going to define this.
I did actually like a Fourier transform here.
It looks
essentially.
This state, I'm going to call this K.
Okay.
Yeah, it does look like a Fourier transform, right? Yeah.
It does.
Right? So indeed. So let's call this state K. And the point is that what this does, it takes each of these L's and it moves it to L plus 1.
Mm-hmm.
So when I act with this operator right here, U on K, I get U acting on K, U acting on K is actually just equal to e to the minus 2 pi I K over n on K. See, this just gets augmented to L plus 1, but this doesn't get augmented. The phase doesn't get augmented. So it's off by a factor of e to the minus 2 pi I K L over n. So, so this actually just says that the eigenvalues, eigenvectors of this U, and this is well known, right? Because this is just you diagonalize the tight binding model for a free particle hopping around in a ring, and that's what you get, right? So this wasn't too hard to do. So, so this makes sense, and of course they do makes sense. It does look like a Fourier transform, right? Because these are just momentum eigenstates for a free particle that's hopping around in a line. It's like looks like a massive particle that's just like hopping along, basically. Okay, so now, then here's the sneaky bit. So let me just, I'm just going to tell you what the eigenstates of HF are simply by pulling it out of a hat.
Proof by intimidation.
Yeah, proof by intimidation. So K is going to be the following. It's going to be the sum over L, and it's going to have the same thing, e to the 2 pi I K L over n. And then you're going to have the register here. This is the clock register. So this would be exactly the same, right? But now we have to worry about the qubit register as well. And this gets tensor product with UL U1 acting on 0, 0, 0. So what happens is this correlates and indeed entangles the correct state of the clock, at time L, with the correct state of the computation at time L, right? Because the correct state of the computation at time L is you perform the first logic gate, the second one up to the Lth one. Isn't that cool?
Yeah.
Yeah.
Right? And then, so, and indeed, we have HF acting on K is just equal to e to the 2 pi I, same thing, minus 2 pi I K over n. There, I diagonalized it for
Wow.
you.
Yeah.
Beautiful.
Yeah, but now that's sort of weird, right? I say, okay, great. So each of these, I have just a particle that's moving along a line, or it could be like an infinite chain. That's okay. And then I have to add, these extra like m qubits to go along with that. But then if I just have just that spectrum, then the computation is isomorphic to just this particle moving along a line, and that's really weird. How can that be, right? Because then that says like a free particle should be doing the computation, and it took me a long time to figure out what was wrong with this. And what's wrong is that in order to calculate, it is indeed true that the state of this quantum computation is isomorphic to the state of a particle moving along a line. But to figure out the isomorphism, you actually have to perform the whole computation, because you've got to figure out what state to correlate with the state of the particle. And so diagonalizing the computation is equivalent to performing all the computations, diagonalizing the final Feynman Hamiltonian. So it doesn't do any good. You actually have to know the answer to all your computations before to do it this way. So that didn't work. However, this has a very nice feature, and I'm pretty sure this paper from 1991 called Quantum Computers and Uncomputability, by the way, that the ground state of this system, which is k is equal to 0, so the ground state of this system is just a uniform superposition of the states where the clock is in the state L together with the qubits are in the correct state at that time, right? And that shows you that, the ground state actually contains the whole computation in it. And indeed, if you were, if you set it up so that after you get the answer, the clock keeps ticking for a long time with the answer in the answer register, and you just make a measurement and you find the clock, the clock is, I should have the answer now, then you actually will know the answer to the computation.
By the way, also, how do you define the clock here? What is like?
Yeah,
the
so
idea of-
Feynman described this as just having It was actually just, I think, you can have a set of zeros and ones. You have zero is no particle, one is one particle. So he had a bunch of qubits, if you like. Not that they were called qubit at that time. The word qubit wasn't coined until Ben Schumacher did it in like 1995 or something like that. So yeah, so then each of these interactions are local, right? Because you say particle moves from this spot to that spot. At the same time, I say do a 2-qubit logic operation. So this trick in this Feynman Hamiltonian, which, as I noted, I mentioned here in this paper in 1991, I think, which was the first, I mean, nobody bothered to diagonalize the Feynman Hamiltonian before, because actually really nobody had ever written paper. There are very few papers on quantum computing at that point. This is what underlies the whole theory of Kataev's theory of quantum Merlin-Arthur proof, so what's called QMA, which says it's analogous to NP, quantum analog to NP completeness. And NP completeness, you say, oh, okay, we're going to, a nice physical way to think of it is we're going to encode the solution to this problem is the ground state of some constrained system, like an icing model, for example, a classical icing model. And then this tells you how you can encode the answer to a quantum computation in the ground state of some system. So it's a very useful observation, this observation.
At what stage of your career were you when you looked at this problem? Was this in your postdoc with
Yeah, it was when I was doing a
Gelman?
postdoc with Murray at Caltech. And then actually what happened is I was frustrated. Oh yeah, the other feature of this, I should say, why does uncomputability get into it? It's because you can kind of see if you set this up. So if the computation is finite, then you can set it up so this whole thing is just periodic in L. If this state is periodic in L, then the spectrum is discrete, right? Because it's periodic in L, so then, n doesn't go to infinity, it only goes up to a certain amount. But if the computation goes on forever, then the spectrum is continuous, which makes sense because the spectrum for a particle hopping along a line is continuous if it goes on forever, and if it's discrete if it just goes around in a circle. And so the question about whether this system, this Feynman Hamiltonian, has a discrete spectrum or a continuous spectrum answers the question of whether the computation halts or not. But figuring out whether a computation halts or not, as Turing famously showed in 1934, is uncomputable. So figuring out the energy gap of this system, whether it's gapped or gapless, is uncomputable. That's why the paper is called Quantum Computers and Uncomputability. But it didn't help very much in terms of like building a quantum computer. This is the kind of thing I feel everybody should know about this Feynman Hamiltonian. This is something everybody should know.
So in the beginning of 90s, were you and the community was looking for the problems that the quantum computer performed better than the classical one?
Well, what community?
There's basically Eckert around that time was going
Deutsch and
around.
Well, Deutsch and, right.
Yeah.
So Deutsch and Joseph was 1991.
And
In
then
fact,
Shor.
well, Shor was 94.
Yeah.
So Shor 94 was like the Grover was 97.
Yeah.
I think
96
Eckert
or
around
97.
that time bringing that to the physicists, the quantum computing notion.
Yeah, well, the first paper that showed something could be done faster was this Deutsch Joseph paper, which I have to say I was the referee for that paper. And I
Which
said,
journal was that?
it was for PRL, and I looked at it. I said, "You mean because you can do this on average in one step instead of 2 steps? That's really impressive." I didn't know.
You weren't impressed.
Did they generalize it in the paper mentioning that they can do it like for?
I think it's worst case exponentially harder. But on average, I didn't know anything about computational complexity. I was like, so you're saying on average it goes faster by a factor of 2? Is that really that impressive? So I think it ended up getting published in Physical Review A instead.
Yeah, it is n by 2, right?
Yeah.
The advantage.
Yeah, but at that point I started, so I said, okay, in terms of actually building this, I've got to think of something else. And so I started teaching myself quantum electrodynamics and atom optical interactions and things like James Cummings model, multi-particle James Cummings model, and what happens when light interacts
Like
with
cavity
spins
QED.
like what's now called cavity QED, exactly.
Oh, what's now called? Okay.
Yeah. So, and then I realized that actually, if you used electromagnetic resonance, like, electromagnetic resonance says, okay, I have got a spin, and it's got a magnetic moment. I put it in the Earth's magnetic field. It will process around at the Larmor frequency, or whatever magnetic field is, that Larmor frequency. And if I drive it on resonance with light at that frequency, the spin will flip. Actually, it's a little, it does something like this. It goes in the co-rotating front, it flips like that. So it flips, and you can rotate it anywhere you want on the so-called block sphere by single qubit operations. That's good. So then you have to, okay, that's good, because you need those for quantum computing. And then the other thing that you needed was something, at that point, this was before it was known that controlled knots and single qubit rotations were universal, so you needed a Toffoli operation. And I realized just from talking with folks who did things like NMR that you could actually do a Toffoli operation in a very straightforward fashion. If you just have 3 qubits that are interacting with each other, then there's a simple procedure that will allow you to flip this one if and only if these other 2 are 1, right? And then I also showed how you could wire these operations together in actually just a homogeneous lattice of quantum systems, and then talk to them globally and then perform universal quantum computation. So that was that took from 1992 to 93. And by that time, by the time I got that paper written, that appeared in Science and in 1993, it was pre-Shor. People did read it pretty seriously because it was like, oh, that's how you build quantum computers. And that's, of course, is how people build quantum computers today, right? Not accidentally. People were not very interested in it, frankly, but it's okay. It was during that whole process of kind of figuring out what kinds of systems you could use to build a quantum computer, I realized, well, actually, if you can zap them with light, and if they interact with each other, you can get them to compute if you talk with them nicely, or as you mentioned, being a quantum masseur, it's like if you just tell them to compute, they're not going to do that. But if you kind of massage them nicely and tickle them in the right fashion with your mathematical fingers and your lasers, then they'll be happy to perform a computation for you. So I think that's when I got the reputation as an atomic masseur, because starting then, even before Shor's algorithm, I started working with these experimentalists doing atom optics, NMR, and superconducting systems. I worked with Hans Moe on what ended up being the second superconducting qubit, because our friends Shensai, Nasunoda, and Nakamoto scooped us by a few months. So I looked at all these systems at nitrogen vacancy diamond, Salim Shahryar, and I figured out how to make nitrogen vacancy diamond commute in the 97 or 98, something like this. And then, so we worked out all these different ways for building quantum computers.
Wow.
Do you have a favorite?
Yeah, what's your
implementation?
Favorite one? Or do you have a bet on those horses?
Yeah, I don't know. I mean, it's hard. I wouldn't know what to bet on these horses because the race just keeps going on. First ion traps kind of were there. Then, of course, the first quantum computations, which Dave Corey and Ike Chuang and Neil Gershenfeld and I performed here at MIT using NMR. But NMR is not scalable, but you could still do the quantum computations. So back in mid-90s, we did the first 2-qubit quantum computations. They did what they were supposed to do, by God. Deutsch-Jozef algorithm actually works in practice. Yeah. I always liked the NV Diamond one, was good because that was fun.
That's what I've been working.
Yeah, his
do my
PhD.
Oh, really? Who you doing your PhD with?
I work in Vlad Shalayev's group. But then for me, it was when I just joined studying like a fresh PhD student, Vlad was like, how about you start a project with color centers while the rest of the group was working on metamaterials and meta services, this hyperbolic metamaterials. So I was basically spearheading that direction in the group, and now I feel like the whole group is now doing different types of color centers and different materials.
So we actually I met Salim Shahryar, who was an expert on NV Diamond. This was in 1997 or something like that. And I just met him at the faculty lunchroom. And it's like, hey, what do you do? Oh, I work on these NV Diamond. What the heck is NV Diamond? It's, okay, well, we've got this diamond crystal, and then there's a defect, which is a vacancy where carbon atoms are missing. And then next to it, there's this defect, which is a nitrogen. There's a nitrogen and a vacancy. And these things behave like super atoms that have a really high dipole moment. You can talk to them directly with lasers. You can read out their state individually. I said, and they also have a very strong dipolar interaction. So I said, we can build a quantum computer out of this, no problem.
Maybe quantum repeaters. Well, not out of nitrogen vacancy centers, but other types.
Well, we had a great, our architecture was great. It was, so nitrogen vacancy, the experimental system we had was this black diamond, which was this diamond that had been blasted in a Soviet era accelerator to create all the vacancies. And so the vacancies were very close to each other. They were like 10 nanometers apart.
Oh,
so
wow.
they interacted
It's
strongly
dense,
with each
yeah.
other. And then the idea is it's also a spectral hole burning material so that the different vacancies have different frequencies. And so you could actually, if you focus in your laser close enough on a spot, on a diffraction limited spot, you can resolve the spectral lines of the individual nitrogen vacancies in that physical spot, which means you can address them individually.
Oh, wow.
And then so we just said, okay, you can address them individually, and then they're interacting with each other. You can find out who's interacting with who. And then that's actually a perfectly reasonable way of building a quantum computer. I think that people are even pursuing this. This was the original architecture.
It's
but
like
I think
in
people
bulk, yeah.
are doing it
NVN
like
samples.
that, yeah. Anyway, yeah, that was very fun. Yeah, I don't know. Of course, my favorite quantum computer is the universe itself. Getting back to that point right there. So during this whole period of figuring out how to take these different systems and build quantum computers, I basically said, oh, what's really going on here? Why can we do this with so many systems? And it's because actually these quantum systems are all just registering information to begin with, like an electron spin up, we call that 0, spin down, we call that 1, spin sideways is 0 and 1 at the same time. And indeed, the fact that quantum mechanical systems store finite amounts of information is the first discovery in quantum mechanics, because that's what Max Planck discovered, right? He figured out when he derived Boltzmann's constant, when he discovered Boltzmann's constant, he said, oh, if things are quantized, then they have a finite and countable number of states, which means the amount of the information is digital and it's finite. That is what's in those original 2 papers in 1900 and 1901. And so actually, the point that we're discovering, okay, not only do they store finite amounts of information, so, we can just say, here's this quantum system that's got 5 bits of information, here's this one that's got 7 bits of information. But the stuff that the work that I'd been doing on making them compute showed that that pretty much any interaction you had between them was sufficient to actually perform a quantum computation. And it was from that actually that I came around to the perspective as this, well, actually the universe as a whole is just really doing a computation, and all we're really doing is kind of, when we build quantum computers like using NMR or building superconducting qubits or using MV diamonds, we're just kind of hacking into some subroutine in this computation and having it perform a computation that we want, right? So it was like the original title I suggested for my book was Hacking the Universe, but somehow I think there was some problems with that actually, like, for instance, hacking, if you translate it directly into Chinese, it sounds like you're like butchering the universe, hacking up into pieces.
Yes, probably most languages.
Yeah. So we went with programming the universe instead.
So looking at the universe as the quantum computer, so every computer, it has a program or a code which it runs.
Yeah.
I guess it's like a philosophical question. So does it generate it on the go, or there's like already a built-in code that it just kind of implements? I guess the code could be the laws of physics. I guess my other question is like, where do the laws of physics come from, and are they stationary or they change even with time?
Yeah, that's a great question. And of course, we don't know whether the laws of physics are stationary or change in time. We don't know whether, for instance, the standard model, which we see to prevail in our visible universe within our horizon, we don't know whether that holds at infinitely far distances or very large distances away. So we don't know very much about that. But one thing we do know is that the laws of physics do support computation. Because, hey, I got a computer, And so we know they support computation. And so we know that the laws of physics, at least the ones we have around here, do support computation. And you can, by setting up a physical system and programming it by preparing its initial state, for instance, you can get it to compute. And so, yes, I sometimes got in trouble about this. My cousin is the head of the anthropology department at Brandeis. And at her wedding, you know how at weddings you have your colleagues and then your family members, but you don't want to have just the colleagues for themselves. They've got to force them to mingle. So
Yes.
I was sort of sacrificed to the anthropologist table. So I was sitting at the anthropologist table. And one of my cousin's close collaborators was Barbara Ehrenreich, who I don't know if you know who she is, but she died recently, but she was a really amazing anthropologist, cultural anthropologist. And she asked me what I did. And it turned out she had a degree in chemistry. So it was I started to describe this. And I described it. I said, well, yeah, so I build quantum computers. And my colleagues and I, we take atoms and we exploit their natural information processing ability to make them compute. And the anthropologists were like, that's horrible. You're exploiting, you're a colonialist, exploiting the atoms. Oh my God, making them compute. That's terrible.
It's against their nature. They do not want that.
That's when I think when I came up with the metaphor, okay, make it more like we kind of like massage the atom.
Right.
So afterwards, it was very funny. Barbara Ehrenreich's companion, who was this older African-American activist from Greensboro, North Carolina, he came up and he put his arm around my shoulder and he said, Seth, the next time you describe what you do, I suggest that you say you empower atoms to compute. Which I've done ever since. It was a beautiful moment in my life. I went just like that, from being an exploiter of atoms to being an empowerer of atoms.
To what extent were you using analog or classical computers at that time in your own work, like in the late 80s, early 90s? Did you even need them for numerical computation?
I try not to program computers unless I have to, because I spend too much time thinking about computers. However, when I got to MIT in 1994, I couldn't get a job to save my life, by the way. Not only was I almost kicked out of graduate school, but then when I started applying for postdocs, when I was getting my PhD, this was 1988, nobody was interested at all. And I'd sent out like 92 applications. And by the way, this was before, this all had to be done by hand, right? And it was like you had to print out the applications and put them in envelopes and stuff like that. I'd received 90 rejections. And I was like, ooh, this is not working very well. And then finally, at the last minute, Rolf Landauer at IBM offered me a job. And then shortly thereafter, Murray Gilman at Caltech offered me a postdoctoral position. That was good. And then I spent 6 years as a postdoc, both at Caltech and Los Alamos and the Santa Fe Institute. You know, I was applying for faculty positions every year, and I never even was interviewed for a position in a physics department. The reason I'm a professor of mechanical engineering is because this was the only academic job I was ever even interviewed for.
That's a pretty...
Yeah, believe me, I don't know. I really I may know a lot about quantum mechanical engineering, but mechanical engineering, no. And so when I got here, my first course that I was teaching was a control theory laboratory. Control theory, a subject about which I knew almost nothing, and a laboratory in which the controllers were these ComDyna analog computers, which are like full of like vacuum tubes with all these knobs and stuff and patches where you like have tunable resistors and tunable capacitors and transformers and op amps, and you like wire them together to simulate other physical systems.
So did you see that for the first time yourself at that point before?
These analog computers, I had to learn them. I had to learn how to do that. It was okay. It was actually turned out to be I was very intimidated, but you know, I started working on it like a month and a half before I had to teach the course. And so by the time I taught the course, it turned out it was kind of fun. Anyway, while I was doing that, so this was in 1994, and maybe 1995, I think, was teaching the course the first time. I said, I wonder how you'd build a quantum version of one of these analog computers. Analog computation was developed here at MIT by Vannevar Bush, and actually Claude Shannon, when he wrote his famous master's thesis, Shannon's master's thesis was, how do you build a digital computer using electronic switches, right? It was like kind of influential. Shannon was working for Vannevar Bush in his analog computer laboratory here. And then I realized, I'd read this paper by Feynman from 1982 about quantum simulation. But this is just, this Feynman paper, all what he says is a great paper, and it gets certainly referenced a lot, but I don't think many people have read it, because what it actually says is, you know, it would be really nice if we had a quantum system we could use to simulate other quantum systems. That would be great, wouldn't it? Okay, now let me tell you about Bell's inequalities. So that's what that Feynman paper is. So I said, well, okay, now we have a notion of quantum computers and how you build them, and here we're trying to build them right now. So how would you actually build a quantum simulator, an analog computer? So then I wrote this paper, Universal Quantum Simulators, I think it came out in 1996 or something like that. It showed how you could do this trick called trotterization and breaking up the dynamics into little tiny steps and doing each tiny step on a quantum computer. So it was kind of the first paper on how you actually make a quantum simulator.
Was it in the paper you were considering to simulate let's say like protons or like spin chain with quantum dots?
Well, yeah. I mean, so the original paper, the 1993 one, said, oh, how do we build a quantum computer out of spin chains or quantum dots, right? And then the later one was, if we had a quantum computer, how would we use it to simulate the dynamics of these systems, right? Of like, for instance, a spin chain or an array of quantum dots. That's closing the loop, right? I mean, it says, okay, these systems are universal for constructing quantum computers, and quantum computers are universal for simulating these quantum systems. So there's a kind of like a general quantum physical notion of universality, which interestingly is not really true classically, right? Because classically, physical systems, classical computers you normally think of as being digital, and classical dynamical systems you think of as being continuous.
Yeah, maybe if you could explain why, if you have, let's say, Hamiltonian's matrix, right? Why not just to try to compute it directly on the classical computer? Why is the simulation is needed? What's the...
Yeah, I mean, it's like, why is it hard to simulate a quantum system? I mean, on a classical computer, I'll just like say it very similar to the way that Feynman does in his nice article on this. I mean, if you have a qubit, right, it's got two states. So we define 0, to just be the state 1, 0. 1 is defined to be the state 0, 1. And a general state for this qubit is psi is equal to alpha times 0 plus beta times 1, which is just alpha beta. And alpha beta are complex numbers. And then because they have a probabilistic interpretation, their norm squared, the sum of their norms is equal to 1. Because this is simply because if I take this qubit that's in this physical condition, this could be like a spin, right? Spin up, it's like this 0, and spin down is 1. And I say, are you spin up or down? And then the probability of getting 0 is this number alpha modulus squared. So that's an alpha modulus squared. That's not very good. Alpha modulus squared, and then the probability for getting 1 is beta modulus squared, and these probabilities have to sum to 1. And indeed, the unitarity of quantum mechanics basically says unitarity simply means that it maintains the norm of these. So this has to be maintained in order for the state to remain physical. That's how you get this evolution. Okay, so so if you have two qubits, so two qubits, they can be in states 0, 0, 0, 1. 1, 0, 1, 1. And so they live, and one qubit lives in the two-dimensional vector space over complex numbers. Two qubits lives in the four-dimensional vector space over complex numbers. And if I have n dot 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 n qubits, this lives in c to the 2 to the n. So it lives in a very high-dimensional vector space over complex numbers. Okay, and the time evolution of a quantum system is given by just a Schrodinger equation, which it says I d psi dt, I guess it's an h bar normally there, is equal to h acting on psi. Whereas if this is n qubits, this is a 2 to the n by 2 to the n matrix. It's actually a sparse matrix, generally, but it's a 2 to the n by 2 to the n matrix. So when you say, okay, yeah, well, we know the Hamiltonian, why don't we just solve this equation? Well, if you're going to do it numerically, then the problem is you have to, numerically integrate a equation over on a 2 to the n dimensional complex vector space, and that uses a lot of memory, not to mention a lot of operations.
So it's more about like the systems of many particles or largely dimensional when it's explodes this exponential term.
That's right. But if you have a quantum computer and you're doing this, right, and let's say you've got a bunch of particles and they're hopping around and interacting with each other, like I think the famously hard thing to do is the Fermi-Hubbard model, right, where it's just a bunch of particles hopping around, fermions hopping around and interacting with each other. What you can do then is to map this onto a quantum computer. Classically, it's very hard to do because it's just a very high-dimensional problem. On a quantum computer, you can map the dynamics of these particles. Each particle gets a few qubits. It tells you like where it is and what it's doing, what state it's in. And then this other particle gets some number of qubits. When then they interact, you have some set of logic operations that cause this small number of qubits to interact with each other number of qubits. And then if you do this in the right way, you can make this, simulated interaction in your quantum computer isomorphic, having the same form as the actual interaction in your system. Yeah. And so that's how you program an arbitrary quantum system into a quantum computer.
Yeah, we also have one of our favorite questions is, if you have unlimited resources, what kind of project would you embark on?
Just how unlimited?
10 plus minus infinity.
10 plus or minus infinity. Unlimited is a strong word.
Let's say unlimited financial resources and infinite graduate students. What would you do?
The smartest graduate students.
Yeah, if I had unlimited financial resources and access to the smartest graduate students, I'd just turn the money over to them and see what they did. Mm-hmm. I think that would be by far the most productive thing to do.
Student project generation.
Yeah, why would I know the right thing to do about that? Yeah, so let's see. We were talking about quantum machine learning. Right, so quantum machine learning, and I note amongst your questions, you also had questions about quantum AI and stuff like that. We started this field of quantum machine learning back around in 2012. And then other people have been working on Jordanis Karanidis, who's a very lovely mathematical physicist in University of Paris. He has done a bunch of these quantum machine learning algorithms, and he just gave a quantum algorithm for doing general pre-trained transformers like GPT, QGPT, QPT.
Just keep adding Q.
QPT, man, QPT. GPQ, I don't know.
I'm introducing QTC. That's the qubit point.
So I don't know about AI in general, but I mean, the thing is that for machine learning, in this case I was describing where you're applying quantum principal component analysis to quantum systems, so it remains exponentially more powerful than any classical algorithm could be. Because a classical algorithm would have to measure the state. You don't even know how to measure the state. You don't know what basis to measure the state in. So you would never, if you're just given a density matrix in some random basis and do classical tomography on it, is it low rank or high rank? Right? You're not going to find that out. So I don't know. This kind of quantum machine learning for learning about quantum systems, that makes sense, right? Quantum systems can generate patterns that are hard to generate classically. So maybe it's the case they can also learn patterns that are hard to learn classically. And then we can show quite simply, we had a series of papers with Christian Wiedberg, actually, because Christian came to me. It was like, you'll detect a pattern here. Christian came to me. I was the chief scientist at Xanadu for like 5 years. And Christian came to me and he said, Seth, let's do quantum generative adversarial networks. I said, great, what are generative adversarial networks? Right? He said, read this paper. I read the paper, said, wow, cool, now I know, sure we can do that. So then we wrote the paper. And we were able to show that if your networks you're doing the analysis on are quantum mechanical, then there are definitely situations where you can do exponentially better quantum mechanically than classically when you're looking at data that comes from a quantum mechanical system. Not surprisingly, really. Mm-hmm. So the real question which is unanswered about quantum machine learning is whether there are advantages for analyzing data that doesn't, on the face of it, have anything to do with quantum mechanics, but just as like linguistic data or something like that, kind of stuff that ChatGPT does so well in its own inimitable and stupid way.
So in allegory of the GAN of the generative adversarial neural nets, and so what if you look? So you look at the universe as the quantum computer, or like one system, and then there is maybe another universe. So could there be like this generative adversarial kind of interplay between them?
Yeah. Okay, yeah. So since I believe that I am the first person to propose the universe as a giant quantum computer, I can hardly object to thinking of the universe as a giant quantum computation, right? That's a good question. Yeah, let's go along those lines. So unlimited resources. Okay, we know stuff like, I think I sent you this paper about computational capacity of the universe, one of whose results is if you wish to simulate, if you have a quantum computer which you wish to use to simulate the universe exactly, then this quantum computer has to be the size of the universe, right? And moreover, any attempt to simulate the universe faster would fail because you need to pack more energy in it, and then the universe would collapse, and you'd have a big crunch, and it wouldn't work. So the universe is actually simulating itself as fast as it's possible to simulate the universe. It's like the most efficient. If you think of the universe as a simulation, the universe itself is its most efficient simulation. I personally don't believe all this stuff that we're just like some twinkle in an alien's eye or some like bits running around in an alien's computer. I don't find it very plausible. Even though I did talk with Nick Bostrom about that. I think actually, you know this paper by Nick Bostrom that I'm referring. Oh yeah, Nick Bostrom, he's a philosopher at Oxford, and he proposed that one of two things is going on. Either, human society, advanced human technological society only has a very short lifespan, or we're just like some kind of simulations in an alien computer.
It's like Matrix.
It's like the Matrix, yeah. And he's managed to convince a lot. This is like something I think Silicon Valley billionaires seem to love this for some reason.
I noticed.
I don't know why. Just by Occam's razor,
yes,
a simpler explanation for what we see going on around us in this office right now is that it is going on.
Yes.
It's a rendering process, right? The ultimate resolution.
The ultimate
the
resolution.
law of parsimony.
Yeah. Rendering, yeah. By the way, rendering was the original industry in Kendall Square here. Because rendering is the process of taking dead animals and boiling them up to make things like fat and soap and stuff like that.
This is the industrial area. We're in a cookie factory.
Yeah, right, exactly, yeah.
Nabisco. Right. I was like, who is this eminent plasma scientist, Nabisco? I gotta look him up.
Yeah, well, and the Genzyme headquarters used to be the world's largest candy factory. It was the every Necco factory, New England Confectionery Company. Every Valentine's Day, they'd make up enough little tiny sugar candy hearts for every human being on the planet. Literally billions. Now they're just like another biotech company, drug discovery. Yeah, so I don't know. So that's a good question. If we say, what could we do if we had a universe to compute with? Or maybe we could even say our universe, it's only 10 to the 42nds old, and it's only like, a few billions, tens of billions of years old, and it's like tens of billions of light years across. What if we had more resources than that? Yeah, I don't know. Probably. Maybe you could test if something's a simulation or not. Because this kind of density matrix exponentiation thing relies on using swap, which is, swap is a unitary transformation. You take whatever is in A and you put it in B, take whatever in B and put it in A, right? So it's a unitary transformation, very simple one. And it's also Hermitian, because if you do it twice, it's its own inverse. Yeah. So if you're unitary and you square to 1, then you are your own inverse. So you must be Hermitian. If somebody gives you a quantum state that they claim is a real one, and you have a copy of the real one, then you could test to see if they're the same by doing a swap test, right? Which is famously simple quantum test.
Or entangled one, not necessarily a copy.
Yeah, well, they give you a copy. It's a quantum state. They say, this is the real quantum state. And you say, I'm not sure I believe you. Let me do a swap test and see. And let's do it with the real one and see what happens.
Maybe it gets some extra phase.
I don't know.
Maybe the alien put some extra phase on it.
Well, I mean, no. Because there are nice things in quantum mechanics, like the no cloning theorem, that prevent things, make it hard, certainly to make copies of unknown states. So it might also be quite hard to make a classical simulation of dynamics of an unknown state. That should be a hard thing to do. I mean, if you have a quantum simulator whose dynamics is just the same thing as the system in question, and somebody gives you the unknown quantum state, and you put it to prepare your quantum simulator, and they let it go, and then you say, okay, yeah, I ran the system, here it is, then that's fine. You can do that. I don't know about getting an unknown simulating an unknown
Speculative.
quantum state.
Yeah, we also like to ask if you have any suggestions or advice for young people who are starting their path in science and technology. Old people.
Yeah. I don't know.
Which
I don't
field
know.
would you pick nowadays if you were to do undergraduate studies again?
Gee, I don't know. I always loved math a lot. And I was really good at math when I was in elementary school. And then when I was in high school, I was good at math. I was like on our math Olympiad team and stuff like that. And I did well in the math Olympiad. And then when I got to college, I was no longer that good at math. And then I was still good at math, right? But, like my abilities became ever more inadequate to do what I had to do. And so now I'm just like really bad at math every day. I come to work, I start trying to figure out what's going on, I fail. But I do like physics and this, this approach to quantizing gravity or strategy for quantizing gravity, of starting from the quantum information side and looking at entanglement and stuff like that, which is how I got into the field in the first place back in 1984. I think that still might work. Of course, we accept from the audience the people who believe they've already quantized gravity.
Do you also think there are still like approachable hanging fruits to get to? Because it seems like also on the other side, a lot of main problems have been solved, and now it's like to get to the next level problems. You need
Diminishing
either to
returns.
construct some big setups like LIGO or Webb telescope or Large Hadron Collider and whatnot. So it already becomes like more as a big agglomeration or like thousands of people working on the project. Is there still any direction which would for physicists to
That's
get
a
into?
good question. I spent all this time as an undergraduate working in the summers on these high energy physics experiments just to make money, right? I need money to like go buy an ice cream cone, Toscaninis, or Ben and Jerry's or Dave's or whatever they were back then. And I was kind of disillusioned by that. The last time I was working with Carlo Rubbia, right, at UA2 or UA1 at CERN, and there were, at that point, there was something like 200 physicists and 200 technicians on the project, and it was definitely big science. And it was really like, after that, I said, this doesn't look like a fun thing to do. So I almost did not do a PhD in physics at all. In fact, I didn't apply to graduate school. And then I did, however, apply to Rhodes and Marshall scholarships. And I was offered a Marshall scholarship, so actually I declined a Rhodes because I wanted to go to Cambridge, which turned out to have been a good idea. It was kind of accidental. And then as I mentioned, I was very lucky to end up doing this MPhil in philosophy of physics, which was really fascinating. And also it really helped studying. A lot of physicists talk about philosophy, and they believe themselves to be philosophical. But it turns out that what philosophers, at least academic philosophers, actually do is kind of different from what physicists think they're doing when they think they're doing philosophy. And it was very useful to find out what it is that philosophy is kind of about, and useful to participate in that. And it certainly propelled me forward learning about these ideas. It was a pretty different context from doing physics. Indeed, Part 3 maths, which I did, was an extremely dull course because it was taught by these famous scientists. Like I was learning general relativity from Gary Gibbons, And it was just kind of a hazing ritual to figure out who gets to do a PhD in England,
Yes,
right?
yes.
From having been there. And so your only purpose there is to try to get an honors degree, be a wrangler, right?
Yeah.
And nothing else matters. And so the classes were extremely dull. The lecturers would have these big stacks of yellowing paper, and they just speak while writing it down. And questions were like discouraged. They didn't want you asking questions because they didn't want to. If you asked questions, there was some interesting problem, and you asked the questions and you disrupted the conveying of the information that would be needed in order to do well on the Part 3 tripos examination, then that was bad. So it was pretty dull, Part 3 then. I've heard it's much better now.
Because they have the tutorials. So my friends who did it, they really like the afternoon tutorial sessions. They have like 2 to 3 classes in the morning and the afternoon.
Do they do that in Part 3? Because they would do that in Part 2, not Part 3. They didn't really have tutorials.
so at least when I was there, it was...
Ah.
They had done this also for part 3.
Oh, good. That's nice. Yeah, that could definitely benefit. Yeah, I don't know. I will say that perhaps because I come from like a huge academic family where basically everybody has a PhD, with the exception of my parents who are high school teachers, but everybody else.
In the sciences as well?
Half of them there were like 30 of aunts, uncles, grandparents, etc., and half of them have PhDs in sciences, half in or medicine or MD PhDs that half in humanities. Yeah. So I had a lot of support growing up. And I did actually pursue things that I wanted to, which were very out of the way. And then I did kind of pay the price, right? Because from the time I decided to work on quantum information, there wasn't even a field called quantum information in 1984. It wasn't even called like a field until like 10 years later, or a decade later. The word qubit wasn't, proposed till 1994. I did suffer a fair amount for doing that, right? I almost got kicked out of graduate school. I had a really hard time getting my first postdoc. I had a really hard time getting a second postdoc. I applied for hundreds and hundreds of junior faculty positions in physics, and I was never interviewed by a physics department. I was really lucky to get a job here at MIT in mechanical engineering. I don't know what they were thinking.
It is still mechanical engineering, different length scale.
Yeah. So it did work out, but it wasn't. It worked out very well, right? But a part of that was just I was kind of lucky. In fact, I was definitely. I think if Peter Shor hadn't come along with his algorithm at that time, I think I might have been in trouble.
Did you ever formulate a plan B?
No, it was kind of like driving a taxi cab, or what other PhD people. When I was getting a PhD in physics, it wasn't a great time to get jobs, and you would meet people who had PhDs in physics driving taxi cabs in New York City. So you can always drive an Uber, man.
You have a fruitful conversation with them too.
But I do think that if you can pick something that you want to work, if you can choose to work on things that you're really interested in, and you're really interested in them just because you find them interesting, not because other people are telling you that they're interesting or not, then that's a good thing to do. And if at that point essentially almost nobody was telling me these things were interesting, though I did rather rapidly, because it was such a small community, get to be friends with all the people who were doing this stuff, like Murray Gell-Mann, Johnny Wheeler, who was very important to me over the course of my career, Wojtek Zurek, all the folks at the Santa Fe Institute working on complex systems and stuff, which is a whole other aspect of my work that has been very fun. So I would say if you are going to work on something that's out there and esoteric because you love it, you should definitely make a big effort to find the other people who love it too and go talk with them. Otherwise, it could be painful.
MIT is a pretty good place to find those people.
Oh yeah. I mean, all these you may notice that I came here, and in short order, we had come up with a bunch of the major paradigms for quantum computing right away, and that was because, I came here and I said, okay, I know how to use electromagnetic resonance to do quantum computing, and I went to Dave Corey, he was Paula Capellar's supervisor. She was his graduate student at the time. I think I even ran into him by accident. We were both at graduation, like the first graduation that I went to. We were in our academic gowns, and we were processing around and sitting on stage and stuff like that. We happened to be next to each other, and I started talking with him about what he was doing. I said, "Oh, that's really good. Maybe we could use this NMR to do quantum computing, because actually you can." Right? I mean, it's here's how it would work. And so we did. And then, I met in short order for Hermann Haus, who was a famous quantum optics guy, and Jeff Shapiro. And then we started working on these quantum optics things, because I had already been working with Jeff Kimball, so I knew a few things about that stuff by that point. And then I ran into Salim Shahriar at the faculty lunchroom. I said, "What does he do?" He said, "Worked on MV Diamond." I said, "What the heck is MV Diamond?" Right? He said, "Oh, that would make a very nice quantum computing
Everything is a quantum computer.
Right?
The universe is a quantum computer.
Right. But the nice thing about MIT is if you say, "Oh, gee, I need to talk with someone who knows about X," right? You're pretty likely to be able to walk down the hall and talk to someone who's the world expert on X. Look at the wonderful folks at the Center for Ultra Cold Atoms, whom I've talked with for many years about all kinds of stuff, right? It's a great place for that. And, people do have a very fine attitude here by and large.
Yes.
So
Much more fun than Harvard.
well, I liked Harvard a lot as an undergraduate. But it is true that it was a different sort of attitude. But I had a good time at Harvard as an undergraduate. In fact, it was quite special because I was in the last class at Harvard where they didn't put lots of restrictions on the courses you could take to, like I was a physics major, so I had to take a fair number of courses in social sciences and a fair number in humanities. And at that point, you could pick which courses you wanted to take. Right after I graduated in '82, they changed it all around, so they made all these core courses that they wanted everybody to do was much more scripted. So I just took these graduate seminars in these different topics. I took a graduate seminar in history and philosophy of science with this I. Bernard Cohen, who was like the famous translator of Isaac Newton and an amazing philosopher of science. Actually, they were like what were the ones that you were saying when you go to the German professor's house and they sit around and smokes?
Oh,
and
a privatissime.
Yeah. These took place at his house, and halfway through they were like a 3-hour seminar, and like 2 hours in, his wife would wheel in this tray with all these fancy liqueurs and delicious desserts and things like that, and then the other graduates would sit around. And I took 2 graduate seminars with Robert Fitzgerald, one on English poetry, on writing prosody, which is how poetry works, the guts of poetry. And another was on Homer, Virgil, and Dante, and he was one of the world's most famous Homer translators. He was the translator of Homer into English at that point. That was a really great course. Yeah, I took a whole bunch of very fine courses there that were very inspiring. So that was a great thing to do. So I had a good time. Because actually the thing is that these big undergraduate courses at Harvard that they kind of push everybody into, they're taught by famous professors, but you don't really have access to that.
Yes.
And a lot of the professors, not surprisingly, what they're really interested in is the stuff they're working on, right? And then that's true here. Like everybody's really interested in the stuff they're working on for some reason. So if you get in the situation where they're actually working on it and talking about their own work, like, Stephen Hawking's seminar on quantum gravity or Robert Fitzgerald's seminar on Homer, Virgil, and Dante, right? Then you're really going to have a fine time. That's
Yes.
way to go. It's nice work if you can get it, and you can get it if you try.
Maybe one of on the nature of consciousness, going a little bit into that.
Oh, yeah, I saw that. Did I send you my article about free will?
No, because that was actually also one of the questions. What is
Oh,
your...
yeah, you should.
I would love
okay.
to read that.
so not all that long ago, like about, I don't know, like 10 or 15 years ago, I wrote for a philosophy of logic conference. It was a course on history, philosophy of logic and computation. Really nice conference where I got to meet all these people who studied with Emil Post and people like that generation of people. I decided to write about free will. Part of it is that lots of people, again, these are kind of physicists who think that they're thinking philosophically, will say things like, let's start from free will from the beginning. So there's free will is this feature that we seem to possess as human beings, which is that we make decisions about what we're going to do. And we're free in these decisions in the sense that we're unimpeded. It's only us who's making the decision. And, we have choices, and it seems that we're free to make these choices. And then there's a clear physics problem with this, which is if you believe that the world is deterministic, then what does it mean to be able to make a choice? Right? And this question is called compatibilism in free will, is having free will compatible with a deterministic universe. It is a very ancient one. If you look at the writings of Epicurus as reported by Lucretius in De Rerum Naturae on the nature of things, in this epic poem about nature, he's talking about atomism, and he says this is all in like exquisite rhyme, poetry, and verse. Right? He says, everything's made out of atoms. And the atoms fall through space in a deterministic fashion. except every now and then one of them gives a slight swerve. The clinamen, the swerve. You may have heard of the swerve. There was recently a best-selling book called The Swerve on exactly this topic. And then Lucretius says, why do the atoms give a little indeterministic swerve? And he said, well, because our free will is our most precious possession as human beings. And in the absence of the swerve, we could not possess free will, right? It's an old argument. And people got particularly, the longer things went on, and particularly after Newton, when people said, moving into the 18th and 19th centuries, where it's like, oh, yeah, look, it looks like things are described by these deterministic differential equations. That's what way everything's playing out. And it did play out that way until really the 20th century, or late 19th century, 20th century, quantum mechanics, yeah. So people were really worried about free will, and many people said we can't have it. And then when quantum mechanics came in, at first Arthur Eddington said, oh, you know, with the advent of quantum mechanics, nature withdraws her objections to free will. And I actually think I really don't understand this argument, right? Because if we're making a decision and we believe we were free to make this decision and we're going to make it one way or another, supposedly on the basis of the merits that we see in the case, like typical decision that I have is like, it's 4 o'clock in the afternoon, I want a cup of coffee. Should it be caffeinated or decaf? It's like, well, decaf is safer. Caffeinated is more exciting, but I don't know. Right?
Living life dangerously.
Right, exactly, right. I know that it can happen if I have a cup of strong coffee at 4 in the afternoon. It'll be midnight. I'll be like, blah, 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 right? So it's a good question, and somehow it doesn't feel right to me that this. I go, oh, well, I'll live dangerously, right? So somehow it doesn't seem right to me that like comes out of some quantum fluctuation. So this paper is called a Turing test for free will. And it says, okay, suppose we have an information processing system. It can be either classical or quantum mechanical, but it could just be classical. And it's making decisions. It's taking in information and has to make decisions to do something. What it says goes, so it's free to do this, right? Now the question is, can this system predict its decision beforehand? Because one of the essential parts of free will, of our experience of free will, and one of the reasons why we believe it to be free, maybe even the reason why we believe it to be free, is that when I'm trying to decide between caffeinated or decaf, I don't know what decision I'm going to make. If I knew what decision I was going to make, I wouldn't be making a decision. I wouldn't have to make a decision, right? So while we're making the decisions, we, the decision makers, we, the deciders, as I think George H.W. Bush used to call himself, like, I am the decider, right? The decider. The deciders we don't seem to be able to predict our decisions. And so what this paper simply says is that if you're a decider, you're capable of universal computation, and then, so for instance, the decider could be a universal Turing machine, then you will not be able to predict your decision. And it just takes the argument that Turing made for the halting problem, and it says your ability to predict the halting problem is, does this particular program halt and give an answer? So you can take this decision problem about you're going to make this decision and say you're going to have some algorithmic way of making this decision, and you're going to make a decision. And what's that decision going to be? And then you can use the same kind of Cantor diagonalization argument that Turing uses to show that that's actually incomputable for you. You yourself can't figure it out. Somebody else who had a better model of you might be able to figure it out, but you can't do it. So it's actually an example of something that's uncomputable to the decision maker. And this is true if you're classical or quantum mechanical. It's this argument. So if you look it up, it's published in the Philosophical Transactions of the Royal Society A. And it's also on the archive, so you can easily find it if you just look Turing test for free will. I've been making this argument for quite a few years now, and I forget when. It's at least more than a dozen years, perhaps a fair amount more. In fact, it even occurs a little bit in my book, this argument, in a verbal form. The theorem is in the paper. I've gotten a lot of buy-in from people like actually Daniel Dennett, who's written several books about free will. I went and presented these ideas at his graduate seminar a couple of times. So I don't think that, I guess I would say, I don't think that this, actually I think free will, feeling that we have free will is perfectly compatible with determinism. The apparent indeterminacy of our free will comes from essentially from uncomputability rather than from any kind of quantum mechanical effect. So I'm going to stand by that until somebody can show me otherwise. And this does have the advantage that you'll, if you read the paper, it should be enjoyable.
It does sound.
Yeah, it has these theorems in it, but the theorems are not particularly hard, and I wrote it in a way that was meant to be readable. Or at any way, some parts are meant to be funny, even if they're not. So that's my take on that part. And okay, so now about consciousness. I actually don't know what consciousness is. In fact, it is not clear to me that when someone like David Chalmers, who is also a friend, I've talked with a lot about this, talks about the hard problem of consciousness, it's not clear to me he's talking about anything, about is it a problem? So, I mean, moreover, it's not even clear to me that people are talking about the same thing at all, right? So we have this spatial awareness of ourselves as existing in the world. There's that kind of consciousness. And that kind of consciousness is really actually possessed by lots of other creatures as well. Like, if you have a squirrel that's running through the woods, it's very aware of itself as an existing creature, sensing in things, processing information. I mean, not explicitly thinking about it, but, it's making decisions about jumping over twigs and stuff like that. And my guess is that when I run through the woods, it's probably very similar experience to that a squirrel, right? Apart from the fact that I don't have a big bushy tail and 4 legs.
Unless you take some psychedelics.
Yeah. Then I might feel I had that. Yeah. Other things that make me feel that it might not be a thing or a problem, this consciousness, is I had a very interesting discussion with my anesthesiologist when I'm about to have my hip replaced. He gave me the option of either having general anesthesia or local anesthesia. It's kind of like, say actually like, hack you open and saw things. I was like, really, I can do local anesthesia?
No way for me.
Yeah,
Absolutely not.
I said, really, which would you do? I asked him. He said, I would do the local anesthesia. And he said, well, for general anesthesia is safe, but it's not, there's still possibilities of complications in general anesthesia. It's like, it used to be a lot more unsafe than it is now. And then he said also, recovering from general anesthesia, particularly for a major operation like this that goes on for hours, can be quite brutal. If you've ever had general anesthesia before, it can be an unpleasant experience when you wake up for a long time afterwards. And the last reason he gave was, plus, I'm going to have to give you a whole bunch of different kinds of drugs because actually, even this is also true for general anesthesia, you can't just give someone something that knocks them out, because an anesthesiologist realized quite a long time ago that the fact that someone's unconscious doesn't mean they may not be feeling pain. Moreover, sometimes, depending on how you knock them out, they may actually remember this pain, and they may be completely traumatized when they wake up. So they have to give you something that makes you not perceive pain. And then it also knocks out your memory of this. And they have to kind of knock out 5 or 6 different things in order to remove the things seem rather, different from each other, to remove your sense of being conscious, which suggests to me that consciousness may be kind of a multipartite thing. And then the other reason that he gave, he said, but the other reason he said I would do this is said, if you do local anesthesia, I'm going to give you this great drug, this really great drug. And when you won't remember what's going on because I can give you something that will have you forget everything that happened during the operation. But as soon as you remember what's going on, you're going to feel great. He said, I guarantee you've never felt so good. And it was true. It turned out to be this one that Michael Jackson killed himself with. I forget what it's called. So they gave me a spinal, like as if I were giving birth or something like that. So I couldn't feel anything from below here. And then they put me on the table and they put a curtain in between me and the people who were sawing and hammering away. In
Yeah.
fact, at a certain point, I don't remember doing this, but at a certain point, apparently, according to one of the physician's assistants afterwards, she said, "Oh yeah, there's a certain point during the operation where we're like going, bang, 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 and you hit me and said, 'Hey, keep it down there. It's too noisy.'"
And you have no recollection of it.
No, I have no recollection of it. No, the first thing I remember is I woke up. I couldn't feel anything because the spinal had kicked in, which was good because, like, for the previous 3 or 4 years, I've been in a lot of pain from the arthritis. And by God, that anesthesiologist, he was right. I was like, felt great. It's like, no pain. Oh, yeah, this is great.
Now we need to know what that was.
Oh, I forgot the name of it. You can find out by, like, Michael Jackson.
Michael
Joy Drug.
Jackson's drug.
Yeah, Michael Jackson's Joy Drug, yeah. Anyway. Yeah, so I don't know what consciousness is. And I'm inclined to think it maybe is not such of a problem. Or as a problem, I think it may be really kind of like overrated as a problem. It might be one of those problems like, like theological problems of times gone by, like how many angels can dance on the head of a pin, which if you believe that there are angels and that they're all powerful except within some limits, like how many of them can dance on the head of a pin, right? That's an important problem, and that's the kind of problem that people like St. Thomas Aquinas and other saintly folks back in the ages of scholastic philosophy in the 1200s spent a lot of time arguing about it, and it seemed to be extremely important.
Yes.
More important than it seems now. And I actually kind of think that this consciousness problem might be like that. That as we find out more about what's going on, this kind of like, oh my God, there's a big problem, this might fade as we understand better what's going on. However, maybe I can close by, and then we need to go get a beer because it's almost 7 o'clock. So I do actually have something to say about quantum mechanics in the brain. First of all, I don't like the whole, Roger Penrose, Stuart Hameroff thing about quantum coherence being important in the assembly and disassembly of microtubules, and so there's like quantum entanglement going on there. Well, I mean, actually, of course, there are a lot of processes in quantum biology that do involve quantum coherence, like photosynthesis, but just simply the dissipative nature of the assembly and disassembly of microtubules, they are doing all kinds of information processing. They're kind of like little cellular automata that do all kinds of cool stuff, but it's really not quantum mechanical. And so I think one has to be really careful about this. However, there is a very cool effect, which is called the quantum question order effect. All right, so now we know in quantum mechanics that because measurements don't commute with each other, if I have a question where, I have a system in a particular state and I ask, first, what does it spin along the z-axis, and then what's it spin along this axis, then I'm going to get different probabilities for the sequence of answers that if I start by asking this axis and then this axis. So the order of questions matters. And the order in which you ask people questions matters too, right? And this is very well known. Like, if you ask people questions about politics, you ask the answers you get will depend a lot on the order that you ask the questions. You probably get any sequence of answers you want if you ask questions in the right order. It's sort of like it's kind of like the watchdog effect or something like that. Now, but the thing is, in quantum mechanics, there's a very specific structure having to do with the linear algebraic nature of quantum mechanics about this question order effect. And I can, since I have a blackboard right here, I can tell you what it is. Suppose we have two questions. They correspond to measurements A and B. Okay. And we're going to talk about this quantum mechanically. So let's just take, we have a state, and A is, these are questions asked for a qubit to a two-level quantum system. This is true for multi-level systems as well. So yes, the answer yes for A corresponds to a projector onto, yes for A. And the answer is yes, no for A. It doesn't even, now I've made projectors that don't even have to be pure states, but we'll make them pure states. That's probability no for A is equal 1 minus probability yes for A. Like maybe. And the same thing for B. Okay? And if A and B don't commute from each other, these projectors don't commute with each other. Right? So let's assume that these are pure state ones. So I have a state where I asked A and I got the answer yes. So actually this would P A yes, if it's a pure state, would in fact equal the projector onto the state. Sorry, I'm not doing a good job here. Right. And similarly for B, right? We have B, yes. And we have A, no. So we have these different states here. Now suppose, let's look at the probability that, now let's look at the quantum question order effect. So I asked A, and I got yes. Now ask B. Now ask B. Now the probability of yes for B, given that I had yes for A when I asked A first, well, I asked A first, so I was in the state yes for A, right? And then now I'm asking if I'm getting yes for B, and then I have to square this. And that's the answer, right?
It's like
Are you okay with this?
conditional.
Yeah, it's a
probability.
conditional probability that I get yes for B when I do B second, given that I asked A first and got the answer yes, right? But note that this is equal to
Maybe.
which is equal to the situation where this is the probability, this is equal to the probability for yes for A. This is for a second question. First. Yes for A for the second question, given that I got yes for B for the first question. Right? So this is a particular pattern, a pattern for the conditional probabilities that is just obeyed by quantum mechanics. Okay, this is nothing strange about that. This has nothing whatsoever to do with consciousness, right? What is strange about this, if you look up the quantum question order effect on like Google Scholar, or ask ChatGPT, God help you. I would worry about. I always worry about like what the chatster is, what its little biases are.
Yes.
So, but if you look it up on Google Scholar, you'll find some nice papers about this. And the funny thing is that, okay, now with human beings, you ask them questions in different order, you get different probabilities. But quite accurately, they obey the same rule. And there's no reason why they should do that, really. I mean, you know, what's going on, we're answering questions in our brain is some like funky, nonlinear response to like, by definition, because the neural circuitry is by definition nonlinear. Otherwise, we wouldn't be universal and couldn't compute our way out of a paper bag.
Maybe some inertia. Like ask a person a question when he answers yes, so that the main question will be also answered yes.
Yeah. Well, I actually have this is the quantum question order effect. So, and this is a known effect. I have an explanation for this, actually, a nice little theory of it. If you ask me a question, like, are you going to have coffee or decaf, right? Like regular or decaf, I kind of mull it over. And so I'm presented with a stimulus. My brain is in a particular state. I'm presented with a stimulus saying, okay, now you've got to ask this other question. So you've got to go from whatever your kind of steady state is beforehand to deciding coffee or not coffee. Right? And let's suppose the first one is, I don't know, do you want cake or no cake? Right? I don't know, right?
Yeah.
So I've asked, I answered, I've got cake. Do I want cake? Yes, I do want cake. And then the question is, do I want caffeinated or decaffeinated coffee with my cake? Okay, I want caffeinated coffee with my cake, right? The idea is this, that there's some intervening, complicated, nonlinear thought process that goes on. But if you just consider the vectors involved to be like the vectors of neural activations, like, you know, what neurons are kind of firing together when you're thinking about the cake question, which is what happens. Like you get clusters of neurons that are firing together, like putting the notion of cake in your mind. And then you look at the vector of activations for neurons for the different answers for the coffee one. Then as long as the probability that you answer yes for the second one, let's say it's more likely if you have a higher overlap for the set of neurons with you that are firing after you're in the first question with the set for yes, rather than the set for no for the second one. It seems plausible that you're more likely to choose yes, because, you know, the number of neurons that need to fire, many of them are already firing. You have less far to go. And so then, if all that you have is you have some function, p of, you know, yes for B given no for or yes for A, is equal to some function of these, you know, the overlap between x, yes, B, and, you know, x, yes for A. That is the linear correlation between these neurons. As long as it's an increasing function of this, then you're going to get this, right? Because this is also equal, because the inner product is symmetric. It doesn't have to have the Born rule. It's not even clear to me that I'm not sure if these guys, the quantum question order effect where they ask people questions, I'm not even sure whether they test the Born rule. But this would explain it, right? Because, and that seems to me plausible, right? This neural activity picture, you have different attractors, you have to go from one set of attractors to another, pick one out of another set of attractors, and if you have greater overlap with it, okay, it's some nonlinear process, but as long as it's just some increasing function.
Maybe minimal energy spent for
I don't
it's
know.
like switching between two
Exactly.
vectors. It's
Exactly.
like,
That's right. I don't, you know, these neurons are already firing. Let's not disturb them.
It would be interesting to test whether this is different for people with neurodegenerative diseases, because, for instance, if you ask them to generate a random sequence of numbers, it will be much more ordered than for someone who doesn't have that.
Oh, that's funny, because my students tell me whenever I say let's pick a random number, they say, you always write the same random number.
You should get checked.
That's, you know, the first computer language I learned, BASIC, right? Which is I know it's like very archaic. If you gave the command random, it would return a random number. But it was always the same random number.
Oh, it's the same seed over and over again?
Yeah, so you had to, in order to get it to be random, you had to say randomize. And when you would randomize, what it would do is it would go look at the clock.
Yeah.
Right, and it would like take the least significant digits of the clock and use it as a seed for a pseudo-random number generator. But if you forgot to common issue a failure for Monte Carlo like programs.
It's always the
you
same.
forgot to say randomize. Hey,
they all ended up in the same spot.
that's crazy. Yeah. Okay, good. So see, I even managed to say, I hope I managed to say something sensible about consciousness.
Absolutely.
I don't think that, and it's funny because it really is not, it's not at all. I would like to emphasize again and again, this is not a quantum mechanical effect in the brain. It's, but because you could say neural systems actually involve these kind of linear operations, like which is the kind of the weight matrix combined with a nonlinear operation, like, you know, a sigmoid activation function or a ReLU or whatever activation function. And so then if indeed the kind of the way that these actual neural networks work is essentially similar to the way that the artificial ones work, which actually is like kind of comparing overlaps of vectors and then passing them through some nonlinear kind of thing, then this same quantum question order effect might also be true for neural networks, classical neural networks that are answering questions, which I've been trying to find a student to work on that, like a Europe or someone to do that particular project.
That sounds like a very fun project.
It would be fun. The problem is formulating it correctly.
Yeah.
As with all these damn project problems.
Setting up the problem right, and then you can just muscle through it.
We have a problem. It's looking for a person.
Do you think if we looked at computational scaling capacity of the brain, if we could get some clues about if we are more like a classical computer, or more like a quantum computer, or more like a
Yeah, I don't know. I mean, it's not clear. right?
neuromorphic computer? Well, it should be a
Well,
neuromorphic computer.
Yeah. I mean, of course, here at MIT, this is where a lot of this stuff happened originally, like back in the 50s, right? Because it's,
The perceptron?
and also
Models.
McCulloch and Pitts, where, McCulloch and Pitts model for, the first model for a neural network was made here. And then the perceptron and Marvin Minsky and those folks started working on things. But just the very notion of having a neural network and trying to program it into computers, that really started here back in the 50s. When I first got here, and actually until about 12 or 15 years ago, there was this amazing faculty member named Jerry Letvin, who was the first person to insert an electrode into a neuron in an operating brain. He was an amazing guy. He was a huge man. And he would tell these stories. I'll imitate him. Jerry Letvin telling stories. We took a frog and we surgically reattached its nasal nerve, olfactory nerve, to its visual cortex.
Why would you do that?
The frog was literally seeing what it smelled. While initially confused, within a few weeks, the frog was indistinguishable from a normal frog.
Oh my God.
Even though it was processing all of its olfactory information through its visual cortex.
Oh, that's hilarious.
Yeah, the most extreme one was like that story of this ilk. You could put, there are several of them. We took a frog, we took its brain and cut it into 8 equal pieces and put them back in random order. While initially confused.
After 2 weeks,
Within
it was
after 2 weeks,
indistinguishable.
indistinguishable from a normal frog. He's very famous for he was part of a very famous hack at MIT. I was actually present for this hack because it occurred when I was a senior at Harvard at the Harvard-Yale game in 1981. In the middle of the Harvard-Yale football game, which is a big deal for people from Harvard and Yale, and like extremely important. At halftime, there was a big explosion in the middle of the field, and then this weather balloon slowly inflated, a huge weather balloon, and it flew up into the air bearing the words MIT.
Wow.
And it was amazing. And I was there. It was like, what the hell? It was great. And there's photographs of this, and like, there were people like laughing and pointing, and the players are like. So the night before, the students who were pulling off this hack, they had to go. They had to go to Harvard Stadium and then like dig a trench and like put in the wires and like
Amazing.
the explosives and the device and everything like that, and then cover it up, and then bring the wires back. And then they had a whole bunch of batteries with them because it was like DC, and it was a long wire, so they had all these batteries. And while they were leaving the stadium, they got caught by the Harvard police, and they had all these batteries with them. And Harvard police thought this was very suspicious, particularly the night before the Harvard-Yale game, as they should have been, because it was true. So the MIT students were from Baker House, and Jerry Letvin was the housemaster at Baker House. And so he got a call from the police saying, we caught these students here with all these batteries, and we find this suspicious. And Letvin said, well, bring them back here and let's find out what's going on. So the Harvard police bring the students over to Baker House, And then, the batteries, and Jerry Lettman's there, and he's wearing like a trench coat. And then the Harvard police say, yeah, we found these students, and they had all these batteries and wires with them. And Lettman says, batteries and wires? And then he says, everybody at MIT carries batteries and wires. But then he opens up his coat, there's all these batteries and wires in his coat. So they let them go. Isn't that a beautiful MIT story?
Now I need to look up the photos.
Yeah. I bet you, if you look online, if you look at Harvard, Yale game, MIT hack, there are photos of it. It's like,
Do they keep the tradition, or what's going on these days with hacking
MIT
culture?
hacks?
Yeah.
They happen
No.
every few years. They tend to be rather spectacular. I mean, if you go to the end of the hallway here, there's this funny police car.
Yeah, I've seen
Yeah.
that one on the
That
photos.
police car was the one that was
On the-
on the roof of the
Great Dome.
of the Great Dome. Yeah, and then there's another in the States.
Cannon?
There's
Canon and Caltech.
that was amazing. Yeah, and since I was at Caltech, when I saw the Caltech cannon over on the dot there, I was like, wow. Yeah, that was an amazing hack. And boy, did it piss off the people at Caltech. Do you know this hack?
I don't know this one.
Okay, so at Caltech, there's this cannon it dates from like the Spanish-American War. And it's on the Caltech campus because the Caltech students stole it from a local military academy and brought it to Caltech and never returned it. So it's a very central part of the Caltech campus, and it's like a sign of their commitment, 100-year, century-old commitment to doing these hacks. And so MIT, these guys, they went to Caltech with a big truck, and they'd forged all these documents saying, we need to take the cannon away from us for refurbishing. And they showed that to the campus police, and they bought that, and they put the big cannon in the truck, and then they drove the cannon from Pasadena, California, over here, and they put it in the big dot, the place in front of the Green Building. It caused a huge stir and fuss, and like people at Caltech couldn't believe they'd been taken advantage of like that. And then after that, for several years after that, when the MIT freshmen arrived, there would be people from Caltech here playing mass tricks on them. I have one of these somewhere because they were saying, free shirts for freshmen, and they were MIT shirts, so that MIT, but they're folded up, and you took them, and you didn't see the back, and if you put it on, it's like it said MIT on the front, and on the back it said, because not everyone can get into Caltech. So there were all these MIT freshmen wandering around with a shirt on. It was great. And I have one from the next year. They were handing out these MIT mugs. And they just like these nice black coffee mugs with MIT on it. Like it was black mugs with MIT in red. But when you put hot water in it, it all changed. So I think they changed the colors completely, and it became this like wild iridescent colors. And it said Caltech, the hotter institute of technology. I've got one of those at home.
That's amazing.
That's a very fine one. Okay, look, it's 7:00. We've been going for a very long time here. It's like under 5 hours.
We're setting a record.
Just barely.
This is the record, yes.
Yeah. Okay, but this is, it was long enough that we probably should have a beer.
That would be great, yes.
Yeah, let's do it.
Yes. Thanks so much for your time.
Yeah.
This has been extremely interesting.